All right, so good afternoon, everyone. I'm Abhiram Ravi from Google, and I'm here with my collaborators Naoshad, Mehta, and Kumar. And we'd like to talk to you a little bit about network efficiency in the context of AI and ML networks. And in particular, we wanted to present an in-band signaling mechanism called congestion signaling, or CSIG, that is designed to help manage traffic more efficiently in these kind of networks. So the context for this talk is the following. In ML infrastructure deployments, especially with the increasing size in models and richness of models, the trend is towards deploying more accelerators and more bandwidth per accelerator. And these ML systems have to inevitably scale horizontally. And at some point, it becomes impractical and really cost inefficient to maintain dedicated networks to handle these workloads. This is especially true for cloud providers who not only have to manage their own internal ML workloads, but also support a number of customer workloads as well. So as a consequence, these workloads need to run and exercise some shared data center network fabric. What this means is that network efficiency over these shared fabrics is really critical for the performance of these workloads. And it's also really hard to achieve this efficiency because these workloads come with a large number of flows, and these flows are not just individually bursty and cause flow collisions, they also participate in large-scale synchronized bursts that stress the network unlike any traditional application has in the past. Even if we look at training alone, network performance directly impacts step time for training. Most training algorithms use some form of barrier collectives, and these barrier collectives are only as fast as their slowest communication channel. This means that they are dependent and sensitive to the true tail, which is the 100th percentile of transfer latency. Even in cases where compute and communication can overlap, these workloads are sensitive to throughput. So how do we achieve such network efficiency in a shared fabric? We rely on a multitude of control systems, right? All the way from congestion control operating at the transport layer to traffic management mechanisms such as load balancing, multipathing, traffic engineering, scheduling, all of these operating at different timescales, but working together to deliver application performance for multiple applications while keeping the underlying shared network efficiently utilized. Now, the trend in link speeds definitely appears to be favorable, with 800 Gbps links being the reality today or close to reality today. But at the same time, we should not take it for granted that we are actually able to use all of this new deployed capacity, especially at fine-grained timescales. Now, in order for these control systems to be able to efficiently utilize this new capacity, they need explicit signals from the fabric. Relying on end-to-end signals and treating the network as a black box, signals like RTT or loss, or even low-resolution fabric signals such as ECN is not sufficient. So what kind of fabric signals do these systems need? Our observation and experience is that early and accurate visibility of bottlenecks experienced by flows is what these control systems need. Because once you know where the bottlenecks are at fine-grained timescales and what the properties of these bottlenecks are, you can then take actions to resolve the bottleneck or to route around the bottleneck or simply respect the bottleneck. Now, when we talk about bottlenecks, what kind of signals are we talking about? So here are three examples of in-band signals that can be used to detect path bottlenecks. Minimum available bandwidth on the path, maximum link utilization across all the links of a flow's path, maximum per hop delay, which captures which hop added the most delay to a given packet along its path. Each of these three signals captures a unique notion of bottleneck for a path, and at the same time has a unique purpose and meaning as to how control systems can use them to better optimize their decisions for performance and efficiency. Now, this list is by no means exhaustive. One could come up with more signals which are useful as well, such as maximum number of flows that share links along the path, or maximum queue depth, or some combination of queue depth and utilization, and so on. Now, how do we make these control systems get visibility into these kind of signals? That is where CSIG comes in. So CSIG is a new in-band signaling protocol, and it is designed to be practical to deploy, especially in a shared heterogeneous data center network, while at the same time being effective in the kind of signals that it carries and its usefulness to applications. Fundamentally, it provides fixed length, simple summaries from path bottlenecks over a dedicated portion of the packet header that we call the CSIG tag. It is designed for a targeted set of use cases around control and debuggability. And it is very much amenable to brownfield deployment because it is backward compatible and interoperable with legacy devices and devices that are already in deployment today. Also, because of its low overhead, it can be deployed without requiring too much heavy lifting on the network, such as a change of MTU or such. Most importantly, CSIG can work in conjunction with any routing or transport protocol that operates above it. So CSIG works alongside TCP. It can work alongside any custom transport implemented over UDP. It can also work alongside any hardware offloaded transport, such as Falcon, which was presented earlier today, or even the Ultra Ethernet transport. Now, to talk a little bit more about the protocol itself, I'll pass it over to Naoshad.
Thank you, Abhiram. So as Abhiram mentioned, we have published a CSIG draft in IETF. And one of the main things that we would like to highlight in that draft was we highlighted the use cases and all that Abhiram mentioned. But an important part of the protocol is the CSIG value structure and how we carry the CSIG packet along the network. So when we talk about the CSIG value structure, we have two variants that we have defined of the CSIG tag, a 4-byte variant and an 8-byte variant. The 4-byte variant was primarily developed in a way that it is compatible with the VLAN tag, and it can be seen as a pass-through and pass-through existing devices that support the VLAN tag. And the CSIG tag value structure is split into 3 different fields. The first field is the signal type. The second one, the signal value, and the third one is the locator metadata. Now, a single CSIG packet can carry 1 signal at a time. So the signal type indicates whether it's available bandwidth or the path delay or the delay on the node, etc. The second one, depending on whether you're on a compact CSIG packet or an expanded format, can be a bucketized, so we support 32 buckets in the compact version, and or it could be a quantized value of the path bottleneck. And whenever we replace or we check the value of the signal value and we need to replace it with the next bottleneck that we encounter in the path, we always record that locator's metadata so that we can identify where the bottleneck is in the network path. So here we talk about the life of a CSIG packet. And CSIG packet is always generated at the host, and it can be used for both source-based congestion control and traffic engineering, as well as destination-based traffic engineering and congestion control. So as the packet traverses through the network, you compare and replace any bottleneck values in the CSIG header. When you reach the end host, the CSIG value is extracted, the locator metadata is identified. If you're doing source-based congestion control or traffic engineering, we take the CSIG value and we have a reflection header that goes back to the source so that the source knows what the path bottleneck was. And we are leaving the reflection header of CSIG outside of the spec and dependent on the transport protocol so that every transport protocol can define its own reflection header. So just to wrap up what CSIG is about, or the benefits of CSIG, we have several use cases of CSIG that we have defined in the IETF draft. But just to highlight the key benefits of this here, we have congestion control, which is a primary use case of CSIG, meant to reduce tail latency and ramp up quickly and safely to all the available bandwidth in the network in the absence of any congestion, or precisely respond to a bottleneck in the network. We can also do a bunch of traffic management with CSIG, and it helps to maximize the goodput of the network. And it can also be used for better network provisioning, where you can identify precise network bottlenecks in the path, use it for capacity planning or network debuggability, and timely provisioning of the repair processes. So with that, I'm going to hand it over to Jay, who will talk a little bit more about how to implement CSIG in hardware.
Thank you, Thank you, Naoshad. So we heard about the use cases where the CSIG will be used. That's what Abhiram covered. And then the protocol specifics that Naoshad covered. What I'm going to talk about is what it takes to implement a protocol like this in hardware. And what I want to highlight in my talk is that how simple it is, how elegant it is to support in the hardware. One of the things which we as a silicon vendor worry about is the cost of implementation. And cost of implementation is not in just in terms of the die size the real estate is going to take, how much power it's going to take, the complexity of the implementation itself. All those make the feature, more cost-effective or costly to implement. And the beauty of the CSIG is that it is so simple and so elegant, then the hardware implementation is very, very easy to do. So broadly speaking, there are 4 different aspects we look at it when we are thinking about a protocol implementation. One is what kind of signals we need. Does the signal need state maintenance in the hardware? State maintenance is very expensive. We have to have enough storage in the hardware. We have to have some kind of lifespan of the information which we have to store. What kind of algorithms we have to support in the hardware, right? Then comes the mathematical functions. Are these signals demanding any special mathematical functions? And finally, which is not so apparent, but is actually very complex, then when the packets traverses the network from one hop to other hop, we have to carry these signals or update these signals at certain offsets. If in a heterogeneous environment, if the packet is going through multiple tunnel domains, then we have to reflect this packet into certain offset into the tunnel packet. And same thing, when the packet goes through the tunnel decap, we have to take the information out and bring it out to a different offset. That is very expensive. That feature we call it an editing function. So if you look here, the signals which we talked about are the available bandwidth, right, or the relative bandwidth, the delay. They are atomic signals. That information is available at that instant. So we don't have to maintain any state. It's very, very simple information. Packet comes in. We have, let's say, continuous bandwidth computation like DRE, which is on a per packet basis at line rate. We compute it, compare it with the incoming packet, see what is the mathematical function we have to apply on that. And as we can see that there are only 4 mathematical functions we are thinking, which is a sum, min, max, and count. Very simple mathematical functions. We apply it, and then we do the read, modify, write, or the update on the packet. So that's the signal. Then Naoshad covered there is a compact format, there is a wider format. And that's done because the information, whatever is computed, is expensive to carry in the packet itself. So we quantize it. We make it compact. Let's say it's a 48-bit information on an 800 gig link. We quantize it, compact it to, let's say, 20 bits. That quantization process also takes some algorithm in the hardware. And in this case, there are only 2 kinds of quantizations we talked. One is the absolute quantization, which is a bucketization. You give a range for a bucket value, min and max. And then you can have a quadratic function, which is, again, a simple quadratic polynomial. And based on that, we can do the quantization. So very, very simple quantization algorithms. Signal functions, updates I already talked about. Then let's go about the propagation. So this is one of the deployment where we see that CSIG domain is traversing multiple tunnels. Packet comes in from the server, goes into a tunnel domain, which again goes into a tunnel domain. And if you see the CSIG tag, it stays at a fixed offset relative to L3 or L4 information. It never changes its offset. It's always at a fixed location, which is close to the top, depending on where we are looking. And because of that, the reflection of this information is extremely easy whenever we are going through the tunnel domains. Same thing, when the tunnel goes to the tunnel decap, we can take this information and put it into the decap packet. So in summary, what I'm saying is the implementation of this protocol in the hardware is extremely simple, very elegant, and very easy to support the complex deployments. So that's on the hardware implementation. We have done a lot of work on this protocol. There are various discussions at different forums. I think, Naoshad, you presented at a OCP Networking Monthly as well. So we have presented it at the networking monthly meeting. Also, this draft is submitted at IETF, and there are a lot of interesting review comments we have got from IPPM and ICCRG, which is the Congestion Control Working Group. Besides that, we are looking for, now this I'm talking about a silicon vendor, we are looking at how more kind of signals a typical ML AI deployment needs. So it's one of the type signals, meaning in the header. We can extend this to new kind of signals. So it's up to us that how we want to expand. So that's one input I'm looking at, if you think that for a given application, this signal is of interest, then it's very easy to support in the protocol, and then we have to see that how we support it in the hardware. Besides that, our plan is that we are going to take this protocol into the SCI community, and we are going to support it as a first-class, congestion control protocol in the SCI logical pipeline. So that work has not started. We'll start that work sometime later this year. Besides anything else, Abhiram, Naoshad, you want to add? Okay, I think that's all from our side. Thank you so much.
I think we have time for one or two questions. Anyone?
You mentioned that you're carrying the CSIG header in the usual locations of VLAN tag. How are you making sure that equipment doesn't get confused and treats a CSIG header as a VLAN tag or vice versa?
Great question. And so what we are doing for that is we are going to define a separate ether type or a separate TPID. And this is going to also be interoperating with the existing VLAN tags on the packet. A lot of details on this are in the interoperability section in the draft, but we can talk offline if you'd like more details.
And Naoshad, if I may ask, so hardware typically support a concept of opaque tags, right? So they can take an incoming tag and pass it as it with some updates, meaning not treat it as a VLAN tag. So that concept also becomes very handy. Yeah.
So actually a couple questions. So you showed something about tunneling and stuff. So that means, are you going across public networks, or this is strictly within the data center itself?
So I think one thing to point out is, if it didn't come across, is L3 encapsulations are pretty commonly used in cloud deployments and traffic engineered domains. So you may have IPv6 and IPv4, IPv6 and IPv6. You may have special encapsulations for encryption at L4 or higher headers. So when designing such a protocol, we wanted to be compatible with each of these different kinds of encapsulations that can exist. And the example that Jay showed was essentially showing that, yes, it works in those settings pretty effectively with simplicity in hardware as well.
Yeah, but that means every node is under your control, because every node has to take this read, modify, write, do the computation, all that, right? So that is all within your own data center.
That's right.
Okay. So and the second question is, once you find out, what action do you take? I mean, do you send a person saying, oh, that router is wasting, or do you reroute packets? I mean, how do you take corrective action?
Yeah, there are, like mentioned, there are a multitude of different control systems that can use these signals. and they all operate at different timescales. You could respond at RTT timescales, even in congestion control. That's where we start. And you could also do at maybe tens of RTTs or hundreds of RTTs. You could do load balancing, multipathing, and traffic engineering. And you could also, for example, use it for debugging and provisioning, which is obviously at a much larger time scale. So there are a number of different use cases, and depending on the signal type, each signal has its own purpose and meaning as to how the control systems can incorporate them.
Okay, thank you.
Let's hear it for Naoshad and Abhiram and Jai. Thank you.